Hi, it's Tim. How do you measure the speed of an object at an exact frozen instant in time? Think about it. Speed inherently requires change. It is a distance traveled over a duration of time. But at a single snapshot, time doesn't pass, and nothing moves. So it seems almost paradoxical to speak of motion at a single point. And yet, this is exactly the puzzle that calculus solves. To understand how, we have to look at curves geometrically. If we zoom in close enough to any smooth curve, it starts to look flat, almost indistinguishable from a straight line. So, the goal of a derivative is simply to find the slope of that line at one specific point, which we call the tangent line. But since a single point cannot give us a slope on its own, we must build it from first principles. Let's trace this out step by step. Suppose we have a curve defined by y equals f of x. We pick our target point, point P, which sits at the coordinates a, f of a. Now, because we can't calculate the slope with just one point, we introduce a second nearby point along the curve, which we will call Q. Let's say Q has an x-coordinate of simply x, meaning its position is x, f of x. If we draw a straight line straight through P and Q, we get a secant line. And calculating the slope of the secant line is straightforward. It is just our classic rise over run. M equals f of x minus f of a divided by x minus a. But here is where the calculus happens. We don't want the slope between two separate points. We want the slope at P. So what if we slide point Q closer and closer along the curve toward P? As x approaches a, the secant line begins to pivot, flattening out until it perfectly matches the tangent line at P. Geometrically, we express this dynamic movement using a limit. M equals the limit of f of x minus f of a divided by x minus a, as x approaches a. Now, on the other hand, there is an alternative and often more powerful way to write the same concept. Instead of using a separate coordinate x, let's define the horizontal distance between our 2 points as a small interval h. Therefore, the coordinate for our second point becomes a plus h. If we substitute this into our original slope formula, the rise becomes f of a plus h minus f of a, and the run is just h. As point Q approaches P, that gap h shrinks down to 0. This gives us our definition of the derivative from first principles, denoted as f prime of a. F prime of a equals the limit of f of a plus h minus f of a divided by h as h approaches 0. To make sure this makes sense practically, let's look at a classic algebraic function before we tackle the really difficult examples. Let's find the derivative of the hyperbola f of x equals 3 over x at the specific point 3, 1. Using our limit definition, where h approaches 0, our value for a is 3. So we can set up our limit like this. F prime of 3 equals the limit of f of 3 plus h minus f of 3 divided by h as h approaches 0. Now, let's substitute our actual function into the setup. We find f prime of 3 equals the limit of 3 over 3 plus h minus 1 all over h as h approaches 0. Right now, we cannot evaluate this limit directly by plugging in h equals 0, because that would cause a division by 0 error. So, we need to apply some basic algebra to clean up the numerator. Let's find a common denominator for the top terms. 3 over 3 plus h minus 1 is equal to 3 minus parenthesis 3 plus h divided by 3 plus h, and it's equal to negative h divided by 3 plus h. Now, if we place this back over our main denominator h, the h terms beautifully cancel each other out. F prime of 3 is now equal to the limit of negative 1 divided by 3 plus h as h approaches 0. And finally, because the division by 0 problem is gone, we can safely evaluate the limit by letting h go to 0. That leaves us with our exact derivative value, which is f prime of 3 equals negative 1 over 3. Now that we have the mechanics down, let's tackle a much more demanding exam-level problem. We want to find the derivative of f of x equals 1 over the square root of x at a general number a, where a is positive. This time, let's use our alternative definition of the derivative to see how the algebra shifts. F prime of a equals the limit of f of x minus f of a divided by x minus a as x approaches a. When we substitute our radical function into this framework, we get a nested fraction structure that looks like this. F prime of a equals the limit of 1 over root x minus 1 over root a divided by x minus a as x approaches a. Again, if we try to let x equals a, right now, the entire expression collapses into an undefined 0 over 0 state. So we must find a way to algebraically rewrite the expression. Let's start by merging the fractions in the numerator using a common denominator of root x times root a. 1 over root x minus 1 over root a equals root a minus root x divided by root x times root a. Let's plug this back into our limit expression. F prime of a equals the limit of root a minus root x divided by root x times root a times the parenthesis of x minus a. This looks slightly better, but we still have a problematic x minus a term sitting in the denominator, causing our division by zero issue. To clear this, we need to eliminate the radicals from the numerator. And the most elegant tool for this is multiplying both the top and bottom by the conjugate of the numerator, which is square root of a plus square root of x. Observe what happens when we expand the top using the difference of squares. Root a minus root x times root a plus root x is equal to a minus x. Now look at how our limit expression transforms. So f prime of a is now equal to the limit of a minus x divided by root x times root a times the parenthesis of x minus a and the parenthesis of root a plus root x. Notice the striking similarity between the top term a minus x and the bottom factor x minus a. They are exact opposites. So if we factor out a negative 1 from the top, we can rewrite a minus x as negative of x minus a. This allows us to cleanly cancel the matching terms out of the equation completely. F prime of a equals limit of negative of x minus a divided by root x times root a times x minus a times root a plus root x, and it becomes the limit of negative 1 divided by root x times root a times the parenthesis of root a plus root x. The division by zero barrier is officially broken. We can now evaluate a limit directly by substituting x equals a wherever an x appears. So f prime of a equals negative 1 divided by root a times the parenthesis of root a plus root a. Because root a times root a simplifies to just a, and root a plus root a is simply 2 root a, our final answer simplifies beautifully down to negative 1 over 2 times a to the power of 3 over 2. What we have just accomplished is the bedrock of all calculus. We moved from calculating average rates of change over an interval to finding an exact instantaneous rate of change at a single point. Every shortcut derivative rule you will learn later, like the power rule or the chain rule, is derived using these exact first principles and algebraic steps. If you found this breakdown valuable and want to truly master calculus from the ground up, make sure to like the video, subscribe to us, and drop a comment below letting us know which complex math topic you want us to deconstruct next. See you in the next one. Bye.